This is the introduction to 8.1 sequences and series. This beginning part here is really important. A sequence is another way of talking about a function, which you can see right here. Function, think of a function with a domain is of the set of positive integers. So instead of using x, though, other letters are used like n or whatever. And instead of using y, we have a sub n. So if you have a sequence with a bunch of numbers in it, starting from the smallest going on up, then in terms of ordered pairs, the first member of the sequence would be 1 comma a sub 1. And then the next ordered pair would be 2 comma a sub 2, and so on. So note that the numbers in this thing the function is not continuous in the sense that it's discrete, goes from term to term, and it climbs by integers. There's not a 1.5 or a 2.5 or a 3.5 or whatever. Functions can be a sequence can be infinite or it can be finite. All right, so let's talk about writing the terms of a sequence. So let's say we want to do the first 4 terms of this sequence. Okay, so a sub n equals 3 times n to the minus 2. Now remember I said the ordered pairs are n comma a sub n. Now this looks just like a linear equation, and that's because it is. Now this is easy to calculate by hand. So if you want to do the first 4 terms, it would be 3 times 1 minus 2, 3 times 2 minus 2, 3 times 3 minus 2, etc. But it's going to get a lot more complicated, and let's start learning how to use the calculator with this, because the calculator will be very handy in working with this stuff. Okay, so I got a picture of this first screen here, and I got the calculator over here. So in order to, there's a couple different ways to put sequences into your calculator and get the calculator to cough them up for you. First thing you may want to do is go to function. We're going to switch from function to sequence and hit enter. And then we're going to go from connected to dot and hit enter. Okay, so let me repeat that. I go up to function, arrow over to sequence, make sure you hit enter. Then arrow down to connected, arrow over to dot, and I hit enter. Okay, so notice that sequence and dot are now lit up. So I'm going to hit second and mode and get out of here. Okay, now the first way I can do this using the calculator, and obviously we already just did this, but let's use the calculator to do this. So we learn how to do it. Second, and then the stat key, and that puts me in the list menu. Okay, I arrow over to ops, and down here at number 5 is sequence, so I hit 5. Now the first thing I'm going to put in is the function rule. You can call this the rule if you want, or the whatever you want to call it. Okay, but this is what's being done to n. So here's n. This is the number in the sequence. This is a sequence number. Okay, we're going to take that sequence number, multiply it by 3, and subtract 2. Now notice that here's n. Instead of having the variable x, we now have the variable n. 3n minus 2. Okay, that's the first thing I'm going to put into the sequence. The second thing I'm going to put in is the variable that I'm using to stand for the sequence number. And that, of course, is n, because I used n right there. Okay, the next thing I'm going to put in is the first value of n in the sequence, and that's number 1. We want the first 4 terms starting at 1, comma, and we want to end at n equals 4. So we're going to begin at n equals 1, we'll end at n equals 4, and then the last parameter that we're going to put in is how many numbers are we incrementing by? Well, that's 1. We're going to do 1, and then 2, and then 3, and then 4. Okay, so then I hit close parenthesis. Now let me go over this again. the first thing I put in is the function rule, 3n minus 2, comma, and then I put in the variable n, and then a comma, and then I put in the first number, the first number in the sequence number, first value for n, the last value for n in the sequence, and then the progression. I'm going up by steps of 1. And I hit enter, and there's my numbers. As you can see, I have right here. Okay. Now, we can also do this in the calculator. So I can hit y equals, and here is n min is 1. We will change that in subsequent problems, but not here. Now I simply put in 3n minus 2. And then if I hit second and graph, then here I want to go, I got to fix this. I'm going to start as 1. It's a problem I do later. Okay, and there's the numbers. Okay, and I got them listed here. You can see them here. Now you can also, for a function like this that's linear, you can graph it, and which I do. Here's the numbers I got from the table. Okay, but you could graph it, and in the window you can see I set the window to 110, 110, and then what, 0.5. And then I graph it. And there you can see the numbers. The graph's not continuous. Okay? Okay, so here's n equals 1, and a sub n equals 1, and here's n equals 2, and a sub n equals, a sub 2 equals, so here n equals 1, a sub 1 equals 1. N equals 2, a sub 2 equals 4. And here's 3. N equals 3, and a sub n is, a sub 3 is 7, and here's n equals 4, and a sub 4 is 10. All right, and we could trace this. Let's hit the trace key. Okay, 1. Okay, n equals 2. Now it's got x, but that'd be a sub n, or y, I should say, 4. That's a sub 2, a sub 3, n equals 3, a sub 3 equals 7, and then n equals 4, a sub 4 equals 10. Now in the calculator, they're not using the letter A, they're using the letter U. Okay, but that's the same as A. Alright, so that's the first example. Enough with that. Okay, now it gets slightly more complicated. A sub n equals 3 plus negative 1 to the n. Now this is very easy to figure out as well. It's going to be, if n is odd, then it's going to be 2, and if n is even, it's going to be 4. So here is, well, I set it up here. Okay, here's the window. I got 110, 1. All right. So when n equals 1, a sub 1 equals 2. Okay, and when a sub 2 is 4, when n equals 2, and when n equals 3, a sub 3 is back to 2 again, and so on. Okay, so it's 2, 4, 2, 4, going back and forth, whether we're adding or subtracting 1 to 3. Again, that would be very easy to figure out manually, and then here's the way I did it, using both the sequence command in the command screen, and then using the calculator as well. Here's on the calculator, here's the window I used, and then here's the table, and then here is the same thing using the sequence command. just let me repeat how to get that sequence command. I'll show you that one more time here. It's second, and then stat, and arrow over to ops, and then you get the sequence command. And you can see the order. First I put in the function, I put in the variable, beginning number, ending number, and the incremental step. All right. Let's write the first 5 numbers of this sequence. Again, very easy to do. 2n, this is number 7, page 577. Very okay. You can just figure this out in your head. Okay, it's 7, 9, 11, 13, and 15. Really nothing to it. And here it is in the calculator. Again, as I've shown you before. Okay, and you can study that more if you want. Example 2, writing the terms of a sequence. It's just a little bit more complicated. All right, so in this case, the sequence, again, you can figure out it's -1 to the n divided by 2n minus 1. As it gets more complicated, there really isn't any point in not using the calculator to figure it out. Let me put this, I'm going to put this one in again. Notice that when I use the sequence command, let me do the calculator here. Let me clear this. Okay, so I got parenthesis, -1, close parenthesis. Okay, now it's raised to the power of n, so up arrow n. Okay, and then it's comma n. Oh, raised to the power of n, sorry, divided by, open parenthesis, 2n minus 1. Okay, and let's make sure I got the function. So -1 to the n divided by 2n minus 1, comma n. Oh, hold on, I'm in the computer here. So, yeah, I'm getting mixed up. Okay. All right, and that's all I got to have. All right, so I hit second, and then here's the table, and there's the numbers. Now, the only thing is, it would be nice to know these numbers. You can pretty much guess what they are in their rational form, that these are all rational numbers. So I use the sequence command so that I can express them in rational form. Let me show you what I mean. So let me clear this. So I'm going to do second and then list, and I'm going to do the sequence command. Number 5. Okay, now I got the -1, so I put that in parenthesis, -1, close parenthesis, up arrow to the n. Okay, divided by, notice I don't have to put this whole thing in parenthesis. This parameter is just simply delimited by the comma. 2n minus 1, close parenthesis. Okay, comma n, comma 1, comma 5, comma 1, close parenthesis. Now I hit enter. Okay, then I can do math and then frac and hit enter again, and now I got everything in rational form, and I can arrow over here and see all the answers. Or I could put the answers into L1 and look at them there using the store key. So I could do, here's store, and then L1. It's another option that I have, and then I just go to stat and L1, and there's the answers right there as well. So there's a lot of different ways to do this with the calculator, depending on what you're trying to get done. So here's number 17, and at first I do it by hand. 1 minus -1 to the n divided by n. Okay, so you got 1 minus -1 to the first, which is 1, and you're going to have 1 minus -1 squared, so you're going to get 0 over 2 is 0, and then 2/3, and then 0, and 2/5, and so on. So you can see the pattern. Okay, so again, I just put it in the calculator, 2, 0, 2/3, 0, 2/5, and so on. And now I didn't bother graphing this, and I'm not going to do any graphing later, because these numbers are going to get weird, and they're not going to look very good on a graph. On the other hand, you want to know what they are, so it's not hard to find out what they are. And so here I put them in the y equals, and then I can see them in the table, where I just use a sequence command and then transform them into rational form. All right, so example 3, finding the nth term of a sequence. So write an expression for the nth term of a to the end of each sequence, 1, 3, 5, 7. So we got a sub 1 equals 1, a sub 2 equals 3, a sub 3 equals 5, a sub 4 equals 7. These are ordered pairs, 1, 1, 2, 3, 3, 5, and 4, 7, where this is n and this is a sub n. So this is 1, a sub 1, 2, a sub 2, 3, a sub 3, and so on. So and this is the change between each term is constant. So this is a linear function. So it's going to be in the form of a sub n equals m times n plus b, where m is the slope and b is the y, is the starting point. So I can find the slope easily. I mean, it clearly is 2. Okay. Then I can use the point slope form to find b, or you can just go back a step or whatever. You can just figure it out in your head or whatever. It gets more complicated than you want it. Anyway, so a sub n equals 2n plus 1. That's the rule. Okay, b. Okay, the difference between each term is not linear. The ordered pair is 1, 1, 2, 3, 4, 17. A sub n closely resembles a squared. Add 1 to n squared to get a sub n. Okay, that's about all we can say about that. Okay, 577, number 39. Okay, the difference between each term is 3. So it's going to be linear again. Here's the ordered pairs. Find the slope. Well, the slope is 3. I don't need to go through that. But I'm just showing it so you know that it does conform to all of the mathematical calculations of a linear function. Okay, recursive. In a recursive sequence, one or more first terms are given. Subsequent terms are defined using one or more previous terms. It's been around for a long time, but recursion is a big, big, big deal now. There's a video here. You do not have to watch it. If you watch it, you're in danger of possibly learning something you never knew anything about before in terms of mathematics, and maybe even having some enjoyment. If you like art, you may enjoy going through this video and going, following the directions and going to this website. Now, you can't see the website in the video. It's all blurry. But here's the website you want to go to. And the video goes through the directions you want to follow for playing with fractals. But, like I said, you don't have to do this. Okay, so a sequence is defined recursively as follows. A sub 1 equals 3. So the first term is given. Here, let me go back here. Did I go through this definition? So in recursion, one or more initial terms are given. Okay, and then you're given a rule that uses previous terms. So in this recursive sequence, a sub 1 equals 3. Now notice we're using the k now instead of a sub n. Okay, a sub k, which is k means the same thing as n. Some number in the sequence, a sub k equals 2 times a times 2 times a sub k minus 1 plus 1. So in other words, it's 2 times the previous term plus 1, where k is greater than or equal to 2. Okay? So a sub 2 equals 2 times a sub 2 minus 1 plus 1, which is 2 times a sub 1 plus 2, which is 2 times 3 plus 1 equals 7. A sub 3 equals 2 times a sub 2 plus 1, which is 2 times 7 plus 1 equals 15, etc. Okay? Notice how quickly the terms in the sequence diverge. All right. Now, so I do this in the computer. You can't, or I haven't been able to figure out how to do recursion using at the command screen using the sequence command. So you got to do this in a calculator. So let's go through this. Okay. So I do y equals, and I'm going to clear this out. Okay. Now, notice that the calculator uses u instead of a. So we're going to put in 2 times. Now, how do we get the letter u up here? The variables u are defined in blue letters right along here. U, V, W. So I hit second, and then I hit U. Not the letter U, which you're going to get with the green key for alpha. Okay, this is very confusing. I'm going to hit the second key, and then I'm going to go to the 7 key, and there is the lowercase u. Now, if I hit alpha, and then the 5 key, that's I notice I get an uppercase u, and that's not the one I want. So I want, let's go back. I'm going to delete this. Go back. I want second, and then I hit the 7 key, and that gives me the u. And that's just going to refer to some number in the sequence. I'm going to open parenthesis, and so sequence number n minus 1. Okay, close parenthesis. And then I'm going to add 1 to twice the previous number in the sequence. Okay, now, when you are doing recursion, you must set a value for n sub n, sub the min. So I got, here is u, and then n min, so this is the beginning number, and it equals, now we got to use the curly brackets, second, and parenthesis, and I put in a 3, and then second, and I'm going to close parenthesis. Okay, so now I'm all set. Okay, now, so I got, the rule is, I'm doing 2 times the previous number in the sequence plus 1. And the initial value is 3. Okay? All right. So now I'm going to hit second, and there's my table, and there's my numbers. Okay. And, okay. That's about it. All right. Now, you can do this manually, if you want. It's just that, notice, it starts, let's suppose you wanted to find the 10th number in the sequence, or first 10 numbers, or whatever. Now you're going to get into something. So anyway, the calculator is there to help you out. Okay. First 5 terms of the recursive sequence. Okay, a sub 1 equals 28. A sub k plus 1 equals a sub k minus 4. So a sub 2 equals a sub 2 minus 1 minus 4, which is 28 minus 4, which is 24. Okay, so we're going 28, 24, 20, 16, and 12. Okay, so in this case, it's the previous number minus 4. Okay, so here's the rule. N minus 1 minus 4. Let me go to here. N minus 1. It's here. It's very similar to the previous one, except there's no 2. And I'm going to go over here, and I'll make this minus 4. This just happens to work out. And then the initial number is 28. Okay, then we hit second and graph, and there we go, 28, and you can see it going down. Okay, moving on. The Fibonacci sequence. All right, now we can have, this is very famous, and anybody who wants to get extra credit or whatever could give us a presentation of this. This has been known for thousands of years. People have known about this thing. It's really a big deal, but we can't get into it right now. So anyway, but it's really a fun thing, and it really models a lot of things that happen in nature, and so on and so on. So they give us the first 2 numbers. A sub 0 is 1, A sub 1 is 1. And then A sub 2 equals the previous 2 numbers, where k is greater than or equal to 2. So A sub 0, now notice we're beginning at 0. Okay, so that's just how they like to do it. So A sub 0 is 1, A sub 1 is 1. A sub 2 is 1 plus 1, which is 2. A sub 3 is 2 plus 1 equals 3. A sub 4, now notice, okay, A sub 2 is the previous 2 numbers, 0 plus 1. Okay? A sub 3 is A sub 2 plus A sub 1. 2 plus 1 is 3. A sub 4 is A plus 3 plus 2. 3 plus 2 is 5. And so on. Okay, now, how do we do this? This has got a wrinkle to it. And let me show you what that is. I'm doing this in the calculator. So we go to y equals, and I'm going to clear this out. And so let's put in our rule. So we're going to put in second 7, that's u, open parenthesis, n minus 1, close parenthesis, plus second u, open parenthesis, n minus 2, close parenthesis. Let me double check that. Okay, so sequence, the prior two terms in the sequence added together, that's what equals the current term. Okay, now here's our initial numbers, 1 and 1. Okay, so we're going to put in 1. So if you have more than one initial number, then you put them into these initial things here, into u parenthesis n min. Okay, so I'm going to close this off with the curly bracket. So I got two initial numbers, 1 and 1. If I had three initial numbers and then it began on like 0, 1, like on the second term or the third term, whatever, then I would have to put three numbers in there. I don't know what the limit is on whatever numbers you can put in. But anyway, so now we're all set, and we'll do second. And there's our numbers in the Fibonacci sequence. And we can go on, down the table or whatever. It's fun to see where it goes and so on, see what the patterns are and all that. There's all sorts of interesting things in there. But like I said, we got to move on. Okay, write the first 5 terms of the recursive sequence. A sub 0 is 1, A sub 1 equals 3. And then, so we can write them out, 4, 7, 11, 18. It's not hard to do. But I want to show you something in the calculator with this, which if you have to do this in the future, you definitely want to know about. So the rule is very simple, right? A sub k equals k minus 2 to k minus 1. So let's actually, here, I wonder if I can undo this. I should have left that in there. Oh well. It's the same as the Fibonacci sequence, except it's 1 and 3. So, but I did it. I deleted it, so I got to go put it back in again. So it's going to be, well, good practice anyway. Open parenthesis, n minus 1, close parenthesis, plus, okay, it's going to be second 7 to get the u, open parenthesis, n minus 2, close parenthesis. Okay, so it's the same as, now, the only thing that's different is that the starting numbers are 1 and 3. Okay, so let's go down here. Now, note this. The numbers have got to be in reverse order. Not 1 comma 3, but 3 comma 1. I don't know why. You would think they want a sub 0 to be 1 and so on. But anyway, you got to put them in 3 comma 1. Took me a while to figure that one out. Okay, so here's second graph. Boom, boom, takes a while. Let's go the thing here because I left it. Okay, so there's our numbers. Okay, all right. So let's move on. Factorial notation. N factorial is defined as n factorial 1 times 2 times 3 times 4 dot 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 n minus 1 times n. 0 factorial is 1. That's a fun proof. That's another thing somebody get credit for, extra credit if they wanted to come in and prove why 0 factorial equals 1. It definitely does. Okay. Now, page 570 examples. Writing the terms of a sequence involving factorials. Write the first 5 terms of a sub 1, a sub n over 2n minus 2 to the n divided by n factorial. Okay, so it's going to be 2 to the 0 over 0 factorial, which is 1 over 1, is 1. So that's, begin with n equals 0. Okay, a sub 1, 2 to the first over 1 factorial, so it's just 2. Then 2 to the n over 2 factorial, 4 over 2 times 2. And then a sub 3 is 4 over 3, 2/3, 4/15, and so on. And then here it is on the calculator. Okay. And going back, now we're back to the easy stuff. Okay. And yeah, so, and you can do this either way. Now the sequence you can do factorial with. As long as it's not recursion, you can use the sequence command. And I express it as a fraction. Okay, so here's 5, the number 63, 1 over n factorial. A sub n, a sub 0 equals 1, 1, 2, 3, 1, 6, 1 24th, and so on. And here it is on the calculator. Okay. Simplifying, okay, now here, let's take a look at this. Okay, 8 factorial over 2 factorial times 6 factorial. Now here's the thing you want to get. 8 factorial equals 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which means it equals 8 times 7 factorial, or 8 times 7 times 6 factorial, or 8 times 6 times 5 factorial, or 8 times 6 times 5 times 4 factorial, etc. Well, you want to take the denominator, or the numerator for that matter, and split them up, factor them into factors that match factors above and below. So I'm taking 8 factorial and I'm going to factor it into 8 times 7 times 6 factorial. Then the 6 factorials cancel out. And so instead of having to do, wow, 8 factorial, it's like some humongous number, and God knows how big 2 factorial times 6 factorial is. This will take me, the rest of my life. But instead, and you don't, put it in the calculator, that's kind of tedious too. But you can do these by hand really fast if you cancel out these factored out similar factorials. So I can't factor them out. So I get 8 times 7 over 2. Well, 2 factorial is simply 2. 2 times 1. So 2 goes into 8 4 times. It's 4 times 7 is 28. Now you can do the same thing symbolically. We got n factorial over n minus 1 factorial. Well, n factorial equals n times n minus 1 times n minus 2 times n minus 3, blah, blah, blah. But we don't have to worry about all those. We got n times n minus 1 factorial. That equals n factorial. So we got n minus 1 factorial over n minus 1 factorial. The n minus 1's cancel out, and we're left with n. So here's number 73. N plus 1 factorial over n factorial. Well, n plus 1 factorial equals n plus 1 times n times n minus 1 times n minus 2 times n minus 3. So in other words, n plus 1 factorial equals n plus 1 times n factorial. The n factorials cancel, and you're left with n plus 1. Summation notation. Okay, the notation for the sum. Now we're talking about adding up the terms of a finite sequence, or infinite for that matter. We use the Greek letter S. And so, what's going on here? We got this little italic I. I is called the index for summation, and it stands for whatever n is, or k, or whatever sequence number you are in the sequence. So if I equals 1, that means the sequence starts at 1. I could start at 0, or could start at 50, or a billion, or Google squared, or whatever you want. But it has to start at a specific number. And it ends at whatever n is. Now, n can be infinity. It can be a specific number. It could be Google squared. It can be whatever. It can be pi, e. Well, it can't be pi or e. But anyway, it's got to be some kind of integer. All right. So here's the generic notation. A sub I is simply the first term. So this expression here, the sum, now that's how we read it. The sum of a sub I with index equals 1 to the n equals a sub 1 plus a sub 2 plus a sub 3 dot 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 plus a sub n. Okay, so in other words, you take all these and add them up together. I is the index of summation. Now this is, by the way, if you're into computer programming, this was the original notation for a loop, where a loop, begin and then end. It begins at a particular number, ends at a particular number, and in the loop you do a particular function. Well, this is how loops work. All activities in computer programming, they all originally were expressed in mathematical terms, and they all come directly out of algebra. And it used to be that all data processing, all computer science was under the direction of the math department. Okay, so I is the index of summation. N is the upper limit of summation. So I equals 1, that would be the begin, and n would be the end of the loop, and then in between, a sub I is what you do in the loop each time over and over again to whatever the index is. All right, so here's example A. I equals 1, 3i, to, and then n equals 5. So what are we doing? We're going to take 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5, add them all together. Okay? Now here's how you do this on the calculator. In case you don't want to do this all by hand. I don't understand why you wouldn't want to. But anyway, let me get out of here. So here's what you do. You hit second and then the stat key, and we're going to go over to the math operation, and we're going to put in 5 for sum. And then we'll go second, and now we're going to put in the sequence, 5. So we're going to add up the sequence, because that's what we're doing, because that's what this symbol means, the sum of a sequence. Okay, and here's our rule, 3 times n, okay. All right, and comma, n is our variable. All right, there we go, comma. And we're beginning at 1, and we're ending at 5. And we're going up by 1 step at a time. Close parenthesis, bingo, and there's our 45. Now you could just run the sequence if you want to know the individual numbers in the thing or whatever. Okay, now you can see with B, B's a little bit more complicated. Okay, so let's do B again. We're going to do second and stat, arrow over to math, and we're going to do 5 for sum, and then second stat over to ops, and 5 for sequence. And then we'll do 1 plus, now they got K here, okay, K is, you can use any letter you want. You can use whatever you want, okay? You could call it a name. You could call it, Miss Piggy. I don't care. It's just, it doesn't matter. It just stands for that word, what the number is. Okay, so we got 1 plus, but in the calculator, you only got one choice, and that's n. Plus 1, n squared. Okay, comma, n, comma, 3. Okay, we're beginning at 3. Comma, we're ending at 6, so we're putting in the 6, and we're going up 1 step at a time, unless we're told otherwise. Hit enter and we get 90. Now that's a heck of a lot easier than adding it all up by hand. Okay, now here's the first 8 terms of 1 over n factorial. Okay, and we'll do this again. Second, stat, arrow over to math, 5. Now this would be a fun thing to program. Let's see, 5 for sum, where you just put in the parameters. Second, stat, ops, to save you a few keystrokes, 5 sequence. Okay, so we got 1 divided by n factorial. We're going to go to math, arrow over to PRB, number 4 for factorial. So again, that was math, arrow over to PRB, and then 4 for factorial. Now I got 2 factorials in there. I got to delete 1. Okay, comma, n, comma. Now notice we're starting at 0. So that 0 is cool. 0, comma, 8, comma, 1. Close parenthesis, hit enter, and there's the answer. Okay. All right. 578. So now we're going to do problem number 87. And here's how I did it using the calculator. Or you can do it by hand or whatever, because it's pretty easy to do. Okay, properties of sums. Okay. Okay, if you're adding up, if you're just doing a sum on a constant from 1 to n, then it's c times n. Okay, now if you're doing a constant times the sum of a sub I, or, where a, whatever a is, then it's c times the sum of a sub I. If you're doing a sum of a sub I plus b sub I, then it's the sum of a sub I plus the sum of b sub I. That might be easier to do, or not, I don't know. And this is a typo. this should be minus, okay, there we go. Hate it when that happens. Okay. All right. The sum of the terms of a finite or infinite series is called a series. Definition of a series. Consider the infinite sequence a sub 1, a sub 2, a sub 3. The sum of the first n terms of a sequence is called a finite series. By the partial sum is denoted by okay, so here's the infinite series. Okay. All right. So we got the sum of 3 over 10 to the I of I. Now this is to the infinity, so we're going to deal with that a little bit later. Okay, now find the third partial sum. So that would be I to, I equals 1 to 3 of 3 over 10 to the I. So it's 3 over 10 plus 3 over 100 plus 3 over 1,000, which equals 0.33. And here's another typo. Good Lord. Okay, that's a plus, not an equals. Okay. Control F4. Okay. 0.3 plus 103, so it's 0.33. Okay. The sum of the series, of the infinite series, is going to be, well, it's going to be 0.33 forever, 0.3 repeating, which is 0.13. In the next example, I'll talk about how we turn, in case you forgot, how you turn a repeating decimal into a rational expression. Find the fourth partial sum and the sum of the infinite series. Okay, so here it is: 6 times 1/10 to the I. Fourth partial sum, you can see is 6 over 10. It's going to be I mean, you don't have to be a genius to see this. Okay, now I did it in the calculator. Okay. Now you can't do infinite series in the calculator. That'd be pretty cool. I really wish they would, but I think I'm going to find other ways to do this. Maybe Wolfram. Now, the sum of the infinite series is going to be 0.6 repeating. Find the rational form of repeating decimal. For those of you that all remember how to do this, you can skip this or fast forward or whatever. X equals 0.6. 10x equals 10 times 0.6 repeating. 10x equals 10 times 0.6 repeating, which is 6.6 repeating. Let's subtract x from both sides. We get 9x equals 6.6 repeating minus 0.6 repeating. 9x equals 6, x equals 2/3. Yay. Okay. Population of the United States from 1980 through 2008 is approximately. Now, this is a polynomial, right? Constant term, first degree, second degree, okay? There's no big deal here. We've seen these before, okay? This is just a different way of looking at it. Okay, A sub n is the population of millions. N is the year, n equals 0 is 1980. Find the last 5 terms, 24, 25, and blah, blah, blah. Okay, now here, I really don't want to mess around with doing this by hand or plugging in numbers or whatever. Let's just go right to the sequence, okay? So I put the sequence in here, okay? And then I stave it to L1, and in L1 I can see my 5 numbers. And remember, these are all in millions. Or I can do it in the calculator, and I can get my 5 numbers. So it's really, okay, so these are either way you want to do it, doesn't matter. Okay, either way is fine. It's just, it's going to be a matter of personal preference. Okay, so 579 number 121, $5,000 compounded quarterly with 3% interest. The balance after n quarters. Now notice they're not doing this they're not throwing in the t for the years. It's 5,000 times 1 plus 03 over 4 to the n equals 1, 2, 3, dot, dot, dot. Compute the first 8 terms and then the 4th term to find the total after 10 years. All right, so first I do it in the computer. 5,000 times 1 plus 03 divided by 4 to the n. And there's it doesn't show 8 years, it only shows 7. You can arrow down, whatever, when you do that. Or I do the sequence. And, blah, blah, blah. And, okay. Oh, and then I scroll down in the table to find it for 40 years, which is, or for, I'm sorry, for 10 years, or 40 quarters, 6741 point, so $6,741.70. Or you could run the sequence command again and just make it for 40, 40 comma 40 comma 1, and that'll give you just one number, 6741.74. Okay, so a lot of different ways to do this. So start the homework, or maybe you have the homework done already, or whatever. So that's it.